So welcome back to part F. So we have finished our control charts, and now we're going to move forward to another topic. But before we do that, I've got some bad news for you. And the bad news is this. Sometimes the control charts can give us an incorrect answer. Because after all, statistical process control is based upon statistics, and that doesn't mean that we are 100% positive on things. So statistically speaking, there's a possibility that if all the data points fall between the two control limits, that the process is out of control, where we've been saying the process is in control. And we refer to this type of error as a type 1 error, or also it is sometimes referred to as the manufacturer's risk. So, in other words, the company manufacturing a product, their control charts could be telling them that everything is lovely, when in fact it's not. And the other type of error that we could have is that if we have one or more data points fall above or below the control limits, we would normally conclude that the process is out of control, but there's a possibility that we're wrong and that the process is in control. Refer to this as a type 2 error. And this is sometimes referred to as the consumer's risk, okay? The consumer's risk. So fortunately, we have a secondary test in order to see if there's something suspicious going on or to validate our original conclusion from our control chart. So this is the slide we started with in this chapter. So the two primary questions: is the process in control? We're still trying to answer that question. Control charts are our primary means of answering that question. We went through the 4 types of control charts. Depending upon what type of data you are measuring, that determines what type of chart you will use. Now we'll talk about run tests. So run tests are another way of answering the same question: is the process in control? Except it uses a different method. So in this slide here, we see that we have a control chart, and I've gone ahead and I've connected the dots in the control chart, which I haven't done that before. But what the run tests are going to be basically trying to do is to tell us, is this pattern, this up and down pattern that we see the data points taking, the moving up and moving down, is that pattern random or is it not random? And if it turns out that it's random, then we know that the variability is due to randomness and therefore the process is in control. But if the pattern is not random, then just the opposite is effect. So the reason why I'm showing you this slide is because we're going to be going through quite a bit of calculations in this part of this chapter, and it's easy to get lost in the woods and forget what we're trying to do in the first place. So if you happen to fall into that category, just remember, all we're trying to do with the run test is determine whether this pattern on this control chart is random or not. So we'll begin our discussion of run tests by defining what a run is. So this is the definition of a run. It is a sequence of observations of one characteristic, followed by a sequence of observations of a different characteristic. So, as a simple example of a run, I ask you to consider the random seating of students in a classroom. So, students sit wherever they wish. There's no assigned seating. And so all the students in a classroom fall into 2 potential characteristics. they're either male or female. So using this example of student sitting in a classroom and everyone either being male and female, let's talk about how we count runs. So a run is a sequence of observations of one characteristic followed by a sequence of observations of a different characteristic. So if you take a look at the bottom of the slide, what I have done is I have come up with a randomized list of seating order of students on the first row in a classroom. So an M represents a male student, an F represents a female student. So reading left to right, we have 2 male students, then we have a female student, then another male student, and then 3 female students after that, followed by 2 male students, and then finally another female student on the end. So the way that I count runs is like this. So I start with the leftmost position. So the male student, that is the beginning of a run. And I'm always comparing the next position to the previous position. And if the next position is the same as the previous position, then that is a continuation of the run. But if that position, if that characteristic is different from the previous characteristic, then that begins a different run. So the second male student, that's the same characteristic, so that's a continuation of the first run. When we go to the third student, that's a female, that's a different characteristic, so that begins a second run. The next student is a male, which is different from the previous student, so that begins another run. The next student is a female student, which is different from the previous student, so that begins another run. Now the next 2 female students are the same as the one that began that run, so that is just a continuation of that run. Then getting toward after the third female student, we have a male student, so that's different. So that begins a new run. Then we have another male student. That's a continuation of that run. And then finally on the end of the row is a female student, which is different from the previous student, and so that is also a run. So now I have identified the runs, so now I just need to count how many there are. So in this example, there are 6 runs. And you're going to need to be able to count runs in order to do the calculations on the run test. Now let's apply this theory of runs to statistical process control. In statistical process control, there are 2 ways of counting runs, and there are 2 characteristics in each method. So the first method is called the up-down method. And in the up-down method, what I'm doing is I am comparing each data point in the control chart to the previous data point and determining whether that data point went up, did it increase in value, or did it go down, did it decrease in value. Now, in this particular method of counting runs, the first data point in the control chart cannot be compared to anything before that because it's the first point. So using the up-down method, I have to start with the second data point. Skip the first data point because I can't compare it to anything, but I can compare the second data point to the first data point. The second way of counting runs is called the above-below, also referred to as the median method. Above, below, or median method. This method is going to compare each data point to the median value. Now you know what median is. Median means that 50% of the values are above this number and 50% are below this number. We're going to compare each data point to the median and determine whether or not that data point is above the median value or below the median value. Now, using the above, below, or the median method, every data point can be compared to the median value. So using this method, I will examine each data point and label it as either above or below the median value. Now, so let's take a look at example here. I'm using the up-down method here. So in the up-down method, I do not consider the first data point. So if I look at the second data point, I see that it is higher than the first, so therefore it must have gone up. So I'm going to label it with a U for up. The next data point compared to the previous one went down, so I'm going to label it with a D. The next one also went down, so it's going to get labeled with a D. And then finally, the last data point went up compared to the previous one, and I'm going to label it with up. So now that I've got the labels on each of these data points, I'm going to go back and I'm going to count the runs. So the second data point is the beginning of the first run. The next one is a different characteristic, so that's the beginning of a second run. The next data point is the same as the previous, so that is a continuation of the second run. And the last data point went up, and up is a different characteristic than the previous one, and so that is the beginning of a new run. So in this example, there are 3 up-down runs. Now let's take a look at an example of the above, below, or the median method. So in this example here, I've got 4 data points. I've indicated what the value of each one is. I've also indicated what the median value is for all 4 of those data points. So the median value is 2.5. So the first data point, comparing 1.8 compared to the median of 2.5, that is below. The second one is also below. The third one is above, and the fourth one is also above. So I've labeled them either above or below the median. Now I'm going to count the runs. So the first data point, I can count it because I can do that in the above-below method. That's the beginning of a run. The second data point is the same characteristic as the first, so that's a continuation of that run. The third data point, that characteristic above is different from the previous one, so that begins a new run. And the fourth one, that characteristic is the same as the previous, and so that also continues a continuation of that run. So in this example, there are 2 above-below runs in this control chart. So again, what the run test is trying to do is trying to look at the patterns and is trying to determine whether these up-down or whether these above-below patterns are truly random. And if they're truly random, then the process must be in control. And if they're not, then just the opposite exists, that it is not in control. So let's take a look at how we would do this, and we'll use our case study of Deluxe Super Steakhouse as an example. So let's take a look at some data. Again, these are internal temperatures of steaks that were cooked median. So in this example here, I have 6 samples, and I have the internal temperature of each steak in that sample. And then on the far right-hand column, you see I have an X bar value. So that is the average for each of those samples. And of course, in an X bar chart, that's what I'm going to be plotting. I'm going to be plotting those X bar values there. So I want to do both a median, that is an up-down, a median above-below, and also an up-down run using this data. and I want to use a z-value of plus or minus 2 as my desired limits. Now, that doesn't mean much to you at this point, so just hang with me on this. We'll come back and talk about these z-values. And the median value of all of my x bars is 149.2. So how do we get the mean of a series of numbers? It's very simple to do in Excel. So if I took all these x bar values shown in this slide, put them into a spreadsheet, and then there's a formula for median, and to just highlight the range of numbers that I want to apply that formula to, I would get 149.2 as the median number. So counting the up, down, and the above, below, or median runs for each. So what this slide shows the x bar values as the first row in the table. So all those are x bars. So in the up, down run method, I can't count the first one because there's nothing to compare to. But I can look at the second and compare it to the first. So 148.3 is definitely less than 148.9, so it must have gone down. 149.9 is greater than 148.3, so it must have gone up. That's why I have a U there. You can look at the rest of these and you can see that it's labeled either up or down by comparing that number to the previous number. Now the last one, it just turned out to be exactly the same number as the previous one, so I'm just going to not count that. It's not going to make any difference in our calculations. I'll just put a space in there. Now, the above-below method, or the median method, every number can be compared to the median, which again is 149.2. So what I've got is below, below, above for the third one, below, above, and above. So now that I have each of the data points labeled either up or down, or above or below the median, I can count the runs. So in the first up-down method, the second data point is the beginning of a run. The third one is a different characteristic, up compared to down. So that's the beginning of another run. The next value characteristic down is different from the previous, so that is a third run. And then the next one is also different from the previous, and that is a fourth run. So there are 4 up-down runs using the above-below method. So we'll start with the below. The second data point is the same characteristic as the first, so that's a continuation of that first run. The third one is above. That's a different characteristic, so that begins a different run. The next data point below is a different characteristic compared to the previous, so that starts another run. The next one, 149.3, is a different characteristic, so that starts another run. And finally, the last one is just a continuation of the previous run. So in the above-below method, I also have 4 runs for each of these. Now, I have put out on the Learning Management System a little procedure for going through a run test. And this is the very first step in the procedure, is to count the runs. So you probably want to take a look at that document. It's a Word document that lists all the steps to go through in the run test, and we've just done step number 1. So let's go to step number 2. And in step number 2, the procedure says to calculate statistically what is the expected number of runs. And what we need to know is what is the number of samples in this data. So if you go back and you take a look at the data that we're using for this, there were 6 different samples that we had. So in this case, big N is equal to 6. So E sub r is the mathematical representation for the expected number of runs. So the expected number of runs using the median or up-down method, the formula is 1 plus n divided by 2, or 1 plus 6 divided by 2, which is 4 runs. So we expected 4 runs. E sub r is 4 runs. The actual number of 4 runs is 4. Well, we probably can know right there that most likely our pattern is random if the actual number of runs and the expected number of runs are the same. But we're going to keep going. We also have a formula for the expected number of runs using the up-down method. That is 2n minus 1 divided by 3. So in that method, we end up with 3.6 runs. Now you'll notice that I did not do any rounding on these runs because that could make a difference in this case. So we don't want to round in this example here. Now we know that we have an expected number of runs. We're assuming that statistically that our distribution is a normal distribution. The expected number of runs is the average or the mean value of that normal distribution, and there is a standard deviation associated with that, with each of those. So we need to calculate next what the standard deviation is of the number of runs. So again, n is equal to 6. We have a formula for standard deviation for the median or up-down method. The square root of n minus 1 divided by 4. And what we end up with is 1.1 runs. So in other words, one standard deviation would be the mean 4 plus 1.1. The standard deviation using the up-down method, a little bit more complicated formula. The square root of 16 times n minus 29 divided by 90, and that turns out to be 0.86 runs. So we have counted the actual runs. We have calculated what the expected number of runs should be. We have calculated what the expected standard deviation should be. So we have one more calculation to do, and that's called the z-test. The z-test. Now remember what this variable z represents. For a lot of students, they have a difficult time with z, but really z is pretty straightforward. Z is nothing more than a distance. It's a distance away from a reference point. A distance away from a reference point. And the normal reference point in the standard deviation is the mean or the average. So how far away from the mean or the average is what we're calculating here? What is the median z value? And the formula for it is little r. Little r represents the actual number of runs minus the expected number of runs divided by the standard deviation. So the actual number of runs using the above, below, or median method was 4. So 4 minus 4, that's going to give you 0. So 0 divided by anything is going to be 0. So 0 divided by 1.1 or anything is going to be 0. In other words, z equals 0. Well, if the distance away from the mean is 0 in this example, that means that this z value sits right on top of the mean. It's right, there's no distance at all. It's right on top of it. The other z-test calculation for the up-down method is shown here. Again, it's the same formula. The only difference is that we're substituting the expected number of runs for the up-down and the standard deviation for the up-down. So in this example here, we do have something other than 0. We have z is equal to plus 0.46. So if z were equal to 1, that would mean 1 standard deviation. So z equal to 0.46, that's about halfway, a distance of about halfway toward the standard deviation. If it was 1, it would be right at the standard deviation. If it's 0, it's right on the mean. It's about halfway between the mean and 1 standard deviation. So the last step in the procedure is to compare these calculated z-values to the specifications, the test specifications in the problem. And the problem stated that we wanted to use a z-value of -2, 2, plus 2. So 0 falls between -2 and +2. So -2 means 2 standard deviations to the left of the mean. +2 means 2 standard deviations to the right of the mean. So for the median, our calculated z-value was 0. And the question is, does this calculated z-value 0, does it fall between -2 and +2? And the answer is yes, it certainly does fall somewhere within that range. And if it does fall within that range, we draw the conclusion that the process, the pattern is random, and therefore the process is in control. Looking at the up-down method, the calculated z-value was 0.46. Now we're going to ask ourselves, is this calculated value 0.46? Does that lie somewhere in the range of -2 to +2? And again, the answer is yes, it does. So again, we will conclude that the pattern is random and also that the process is in control. So this concludes this part, and we have one more part, so please continue to it.